This is the lecture on section 9.1, your introduction to functions in this course. And before we actually talk about functions, we're going to talk about a more general relationship, what's called a relation. So, relations. By definition, we have a relation, or sometimes called a relationship, is a correspondence between a set of inputs x, called the domain, and a set of output, or y values, called the range. And so below here what I have is usually what's called a kidney bean blob diagram. On the left I have a kidney bean shape, on the right I have a blob, and I have a collection of numbers. And they could be more complicated or less complicated than the collection of numbers I have, but what we're going to do is we're going to make a correspondence between these sets. We're going to make a relation. And how we do that is pretty straightforward. You can visually represent this between the kidney bean and the blob by picking a number over here and then picking a number on the range. So pick a number from the range, pick a number from the domain, and connect them. There you go. And so that is a correspondence between those two values. We can choose some other relationships here. Maybe 1/2 is related to the number 8. And it doesn't have to be that 1/2 and 8 are the only two correspondents that use those values. That is to say, we could have 1/2 also matched up with 4. Or we could have 3 matched up with 5. Sorry, -3 matched up with 5. And we could also have -3 matched up with -3. That is to say, this relationship is just a rule for matching up numerical values on the left with numerical values on the right. And that can be a very straightforward rule. It can be a very complicated rule. And this is just one possible relation between these values. For example, if I move this over here, duplicate it, see if I can fit it on here. I could just as easily choose a different relationship between all these values. Let's see. So let's see. Let's get some different colors here. Maybe I want to do something as straightforward as 0 gets matched to 8. And 2 gets matched up with 6. Oops. 2 and 6. Or 1/2, come on, 1/2, -3. And maybe you can see where this is going. Not that big of a deal. -3 and 4. And we don't have to actually use every single value, but if we wanted to, I guess we could take this 5 and also match it up with 4. No big deal, no harm, no foul. But there it is. And so we might give these relationships a different name, even though they involve the same sort of input versus output values. And maybe I should write that down. These are the quote-unquote inputs, although it's not strictly necessary here. And the quote-unquote outputs, just so that we associate them with the domain and the range. Inputs, outputs. What I'm getting at here is even though we have the same collection of numbers in both scenarios, these are different relationships because they're different rules that match up the numbers in different ways. And we might give these names. We might say this is relationship A and this is relationship B. So those are the basics, and we can fundamentally represent a relationship in 3 ways. I know I just did one, kidney bean and blob, but we don't technically usually work with the kidney bean and blob diagram. So what we can do is we can talk about how to represent them what's called, in the first way, numerically, and this is as ordered pairs of the form x comma y in parentheses. Now don't get that confused with the intervals that we've been talking about. This is not an interval. So I know it's kind of an abuse of notation. Not an interval. So be careful. Now in this case, we could go ahead and list both of these relationships. I could say that A is a collection of ordered pairs, and it looks like A is 0 is matched up with -3. 1/2 was matched up with 8. 1/2 was also matched up with 4. -3 was matched up with -3. And 5 was matched up with -3. Okay, and maybe I should move some of this other stuff down. We're going to need some more room here. Okay, I could also talk about relationship B. That's a collection of ordered pairs. Now I'm looking over here, and 0 versus 8, and 2 versus 6. When the input is 1/2, the output is -3. When the input is -3, the output is 4. And when the input is 5, the output is 4. And those are your basic rules for those two relationships that I have above. Now, we often talk about the domain and range of each one of these, looking at just these ordered pairs. The domain of A can be rewritten as a collection of just values. So be careful here. I'm using these squirrely braces here. But in the first one, A is a collection of ordered pairs, whereas the domain is just a collection of all of the inputs. So if I were to color code this here, the domain of A is in green, and we would just list these out maybe without repetition and in no particular order: 0, 1/2, -3, and 5. That is the domain of A, the values that we are using as inputs. Whereas the Y values that I'm color coding in blue here are known as the range of A. And that set is -3, 8, 4. And you'll notice that there are only 3 values there. Even though I have 5 ordered pairs, 1, 2, 3, 4, 5, -3 is repeated 3 times. And so I only have 3 distinct or different domain or range values, excuse me. The same will be true down here for B if we talk about the domain of relationship B. That will be the collection 0, 2, 1/2, -3, and 5. That is all of the X values or all of the inputs. And let's see, my range values are 8, 6, -3, 4, and 4. So the range of B is the collection 8, 6, -3, 4. So there you have it. There are 2 different relationships that kind of use that same kidney bean blob diagram from up above, but in a very different way, with a different rule or different correspondence between the inputs and the outputs. So there you go. It's pretty straightforward. We can also represent these relationships graphically. Let me move this down out of the way here. Let's see. For A, I'm going to need to have a... I'm going to have to move this down a little bit here. Let's see. Let me draw an XY axis here. Maybe that's a little too big, but there we go. X, Y, 0. And if I look back at these ordered pairs, I can simply graph them. This is, let me move this guy down here. This is my relationship for A. And so 0, negative 3 is here. 1/2, comma 8. 1, 2, 3, 4, 5, 6, 7, 8. Of course, that's in the way. Come on. 8. Let's get that y back there on the other side. Okay. So this was 0, negative 3. This was 1/2, 8. We also have 1/2, comma 4, which is right there. Negative 3, negative 3, which is down there. And then 1, 2, 3, 4, 5, negative 3. And let me label all of these here. Let's see. This is at 4. This is 1/2, comma 4. This is 5, negative 3. This is negative 3, negative 3. And those red dots, this is at 1/2, I suppose. And those 5 red dots represent the graph of this relationship. Not too bad. Plotting points, pretty straightforward. Let's graph B here. For relationship B, let's draw another XY axis. Oops, I don't know why I put Y over there. Y axis, 0. And we'll start plotting points. Let's do this in a different color, though. Our first input is 0, comma 8. 1, 2, 3, 4, 5, 6, 7, 8. That's 0, 8. Our next one is 2, 6. 1, 2, 3, 4, 5, 6. 1/2, negative 3. This is right in the middle there. Let's see. 1/2, negative 3. Negative 3, 4 is back 3, up 4, and then 5, 1, 2, 3, 4, 5, 2, 3, 4 is right there. And you can see, if you look at both of these, they're very different pictures. That is to say, they are a collection of different ordered pairs. So, that's how you can represent a relationship graphically. The third way to represent it is what's called analytically or algebraically, and so we might say by the formula here is probably what some people are thinking. For example, you might define this relationship not by the numerical values you're actually using, but the rule itself between these numerical values, by the formula or by the rule itself, like y equals x squared. That's a rule. It doesn't tell you what the x's and y's are, but it tells you the rule between the x's and y's. And what you can do is then, this rule allows you to generate your own list of ordered pairs. For example, this is sometimes referred to as an XY chart. And you can just pick a bunch of x values, negative 2, negative 1, 0, 1, 2, 3. And then, of course, you can go through here and take the x value and say, well, y is then negative 2 squared, which is 4, negative 1 squared, which is 1, 0 squared, which is 0, 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, and that turns these into the ordered pairs, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9. And so this rule allows you to generate your own list of ordered pairs and then graph those ordered pairs. So we might be able to plot those here. Let's see. Here's the x-axis, here's the y-axis. One of my ordered pairs is 0, 0. One of them is 1, 1. Negative 1, positive 1. Not sure why I wrote it like that. 2, 4. Negative 2, 4. And then 3, 9 is kind of way off my chart there, so I'll leave it off. And then if we connect these dots here, how do I know they're connected? Well, that's a good point. You could continue this chart here, and you could say things like, well, what if I plug in a half? And then I get out a fourth, and I get the ordered pair 1/2, 1/4, and so on and so forth. And so you can begin to plot all these intermediate points that are also on this curve that we didn't necessarily take the time to fill out our chart with. But that's what y equals x squared looks like. There you have it. We have our domain and our range. Not domain and range. Sorry, we have our inputs and our outputs in this table of values here. And we have the graph of that relationship here. Okay. So those are the basics. Again, you can represent the relationship numerically by the ordered pairs. You can represent them graphically by the picture, and you can represent them analytically or algebraically by the formula or the general rule that relates the inputs and outputs.